We ask a lot of our screens today. Whether we are color grading a feature film or reacting to a split-second movement in a game, delivering on those demands requires building a display that generates light completely differently from the monitors of the past. This image shows a typical editing suite, where professional creators often run into the limits of older liquid crystal displays. LCDs rely on a bulky, always-on backlight, which pushes illumination through the entire screen, and inevitably washed out deep shadows, making accurate color correction incredibly difficult. Over in the competitive gaming space, players face a different physical bottleneck. The liquid crystals inside traditional displays physically change state to produce an image, and that mechanical movement is slow enough to introduce motion blur and ghosting during fast action. And out in public spaces, standard screens present a glaring security flaw. Because older displays are designed with wide viewing angles, anyone standing nearby on a crowded train can easily read sensitive information right over your shoulder. Fixing these issues, poor contrast, sluggish response times, and zero privacy, means we have to abandon the idea of applying top-down filters. Instead, display engineers had to figure out entirely new ways to manipulate light at the absolute smallest microscopic subpixel scale. This animated diagram breaks down the microscopic sandwich structure of an organic light-emitting diode, or OLED. We start with a foundational substrate, followed by an anode, a conductive layer, an emissive layer, and finally, a cathode. When an electrical voltage is applied to this stack, a reaction begins. The top cathode injects negative electrons downwards, while the bottom anode extracts electrons, creating positively charged voids, or holes, that move upwards. The process of electrophosphorescence begins when electrostatic forces draw those opposing charges together until they crash into each other inside the middle emissive layer. This collision forms a highly unstable, vibrating particle known as an exciton. To stabilize itself, that exciton violently releases its excess energy as a single photon of light. The exact color of that light is determined by the energy band gap equation, E equals hc over lambda, which allows engineers to dictate whether the resulting subpixel glows pure red, green, or blue. Because this light is generated chemically from nothing, the screen achieves absolute control over every individual microscopic dot, completely removing the need for a global backlight. This split-screen comparison illustrates the concept of an infinite contrast ratio. By simply preventing that electron-hole collision in specific areas, an OLED panel leaves those individual pixels entirely dead and dark, resulting in the true inky blacks you see on the left. For visual designers, that mathematical precision ensures shadows aren't washed out. When combined with a 100% DCI-P3 color gamut, the incredibly wide color space used as the standard in digital cinema, artists can finally trust that their color correction is perfectly reliable. Gamers benefit equally from this microscopic physics. Because the electron-hole reaction is near instantaneous and doesn't rely on slow liquid crystals changing shape, pixel response times drop below 0.1 milliseconds, eliminating motion blur during competitive play. The path to these modern capabilities took decades of refinement. If we look at this collection of early 2000s MP3 players, we see the commercial infancy of the technology, back when early OLEDs suffered from rapid color degradation. It took the invention of modern LTPO backplanes, a display technology that allows for highly variable refresh rates, to solve those lifespan issues. Mastering this microscopic speed and contrast scaled OLED into the standard for flagship smartphones and large format displays, but it left one major vulnerability: a perfect image that anyone nearby could easily steal a glance at. Historically, solving that privacy problem required applying a thick, polarized plastic sticker directly over the screen. These physical films ruined the viewing experience by tanking peak brightness and distorting the color accuracy of the panel beneath. With the Galaxy S26 Ultra, Samsung Display solved this at the hardware level, moving the privacy mechanism away from the top glass, and built it directly into the black matrix, which is the physical microscopic grid that separates the red, green, and blue subpixels. This top-down view shows the Flex Magic Pixel architecture. Instead of a uniform layout, it features distinct wide and narrow subpixels. They then built physical light-blocking structures around the narrow pixels, acting like microscopic blinders to restrict light travel. This diagram illustrates the screen's normal state, with privacy mode off. Both the wide and narrow pixels fire together, scattering light brightly in all directions, just like a standard premium OLED panel. Because this grid is hardware integrated, it ties directly into the operating system's AI. The phone automatically engages privacy mode when a user opens a banking app or types a password. The display disables the wide pixels entirely. Only the shielded, narrow pixels remain active, channeling light strictly forward, preventing lateral bleeding. The physical result is stark. While the user looking head-on sees crystal clear content, independent testing shows that screen brightness drops to just 3.5% at a 45-degree angle. To an onlooker trying to shoulder surf, the screen simply appears black. By mastering light generation at the quantum and subpixel scales, OLED technology has matured into a system that produces flawless visuals while physically shielding a user's private data from the environment.